Welcome to ECE 302. This is lecture 5.2 on joint expectation. I'm Professor Stanley Chan. Today we're going to look at a second topic in chapter 5, which is the topic on joint expectation. So in the last lecture, we learned about the joint distribution. We learned about the PDF, the PMF, and also the CDF in the case of two random variables. So in today, we want to learn about how to take expectations of a pair of random variables. So if you recall the definition of a expectation, this is the definition. We have a PDF, which is given by fx, and then we have the value x. Then we integrate this x times fx over all the possible states for x, and then we call this as the expectation. This can also be seen if you try to plot the PDF here, and then you say that this is my current state value, and then I multiply the height of this PDF. That will give me some number, and then I'm going to integrate from here to here. That will give me the average, okay, or the mean, or we call the expectation. So this is for the one variable case. We ask, how are we going to generalize this concept of expectation to two variables? In particular, how are you going to define things like this, expectation between x and y? So it turns out that the expectation for x and y, or what we call the joint expectation, is defined as the expectation of x times y. So if you follow what we have discussed previously in the last lecture, we have defined a thing called a joint PMF, or this is we call it the joint PDF. Now, if you want to take the expectation of x times y, very naturally you can follow the one-dimensional case. You have a PDF of a PMF. You multiply with whatever you want to calculate in the expectation. In our case, it would be the product of x and y, and therefore you have x times y. And then you multiply that with the this PMF. This is the joint PMF. Then you sum over all the possible states of x and y. You will get the expectation. Or in the continuous case, you're going to multiply the x and y with the PDF, and then you integrate x and integrate y. You'll be able to get the expectation of x times y for the pair of continuous random variables. So at a high level, this kind of extension from one variable to two variables seems to be straightforward. However, the deeper question that most people do not pay attention to is, why are we defining the joint expectation as the product of x and y? Right? Would you ever wonder, why are we defining the joint expectation of x times y, but not x plus y, x minus y, or x divided by y? Why are we defining the joint expectation as x times y? Is there any meaning associated with this expectation of x times y? And some people call this as the correlation, okay, correlation between x and y. And how can it ever tell us the correlation between two variables? So today's lecture, we are going to answer this question. I want to give you a much more geometric or pictorial meaning of the reason why we want to define joint expectation as x times y, and then we take the expectation. Something that you would normally not find in other lectures. So to just make sure that you are on the same page with us, let me just go through a very simple example. Here is a pair of random variable. We have x and y. X denotes a coin flip, and then y denotes a dice. We want to compute the joint expectation of x times y. In the last lecture, we have studied this example, and we know that the joint PMF is given by this table, where you have the first variable x, the second variable y, and then they're given by this table that contains 12 numbers. And since we assume that X and Y are fair dice and fair coin respectively, so we have the numbers being 1 over 12 for each of these entries. So we ask, how do we calculate this joint expectation, which is the expectation of X times Y? Now, if you follow our definition, you can see that we have to take the take the summation of X times Y, and then times this joint PMF. So how do we do that? Well, we will have, let's look at the first row, right? So you have X, which is 0, and then times Y, which is 1, and then you have the probability, which is 1 over 12. Right? You see that you have X value, Y value, and then you have the PDF. Okay, and then you have X is still 0, Y now goes to 2, the probability is 1/12. So that goes to this entry. And then you sum everything up, and then you go to the last one. So it will be 0 times 6 times 1 over 12. And that accounts for the first row. Now, for the second row, it will be similar. It will be 1 times 1 times 1 over 12 plus 1 times 2 times 1 over 12 plus etc. Until the last one, you have 1 times 6 times 1 over 12. Okay, so you add everything up, and then you will see that the first row, it will all go to 0. And then the second row, when you add all these numbers up, it will be 1 plus 2 plus dot 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 plus all the way to 6 divided by 12. And then if you do the calculation correctly, you'll be able to find this number, which is 21 divided by 12. Okay, so I hope that you can see that this joint expectation is really nothing more complicated than just looking at the PMF or PDF, and then you multiply the number with the corresponding PMF and PDF. You sum everyone up, you'll be able to get the number, which is the expectation of the product of X and Y. Alright, so let's look at the outline of today's lecture. In today's lecture, we are mostly interested in understanding the joint expectation. Okay, we want to know what is joint expectation, and then why do we define the joint expectation as the expectation of X times Y. Independence, covariance, correlation, these concepts we will discuss them in the following lecture. Okay, so this is the goal of today's lecture, which is really to go through the underlying reasons of why we are defining joint expectation this way. Okay, so let us try to understand the meaning of expectation of X times Y. So, what is this expectation of X times Y? If we follow the previous example, we know that it is really just defined as X times Y times the PMF evaluated at the X and Y correspondingly. Okay, here I'm just using a notation of Xi and Yj to say that I have n numbers of I and then n numbers of j, and they have different state values. Okay, because it's not necessarily going from 1 to 6 in the dice roll. You can have 1, 3, 5, 7, 9, and so on. Okay, and so this is a little bit more general notation. And then the other states, X and Y, they can be thought as the coordinates of all the possible values that you're looking at. Now, the interesting thing is about the summation. How would you understand the summation? Well, this summation, if you think about it deeper, you can actually represent this summation in a matrix and a vector multiplication. So let me show you how this can ever be done. So here is the joint PMF, which is a two-dimensional function, and it has n states of X and states of Y. I can write it as the a matrix in this form. So you have n rows and n columns. Each entry would be a X and a Y. Okay, so it is indexed by X and Y. For example, the first entry will be PXY evaluated at X1, Y1. This entry says that I'm going to look at the joint PMF, and I have xn and y2 are evaluated. Okay, so this will give you really a matrix representation of all the possible values of your PMF. All right, so this is so far so good. Now let us understand how you can handle this summation. It turns out that this summation can actually be written as the following. You start with a column vector of y1 through yn. These are what? Well, these are the state values of your y random variable. Okay, so think about here, you have a random variable y. Y is a random variable, and therefore it has a histogram, or we call it the probability mass function. So this is the PMF of y. Now you have values of y1, y2, y3, and y4, and so on. These values will go to here. Okay, so these are all the possible state of the random variable y. Similarly, you can define the vector that contains all the state of the random variable x. That will give you another vector, which I call it the row vector. You have x1 through xn. Then I put them into this matrix vector multiplication of x transpose p and y. Now, let us do some quick calculation and see if this matrix vector multiplication, the thing that I'm proposing here, will make sense. Let's look at this computation. You have p times y. So how do we get the first entry? It would be this number times y1. So you have y1 times the p of xy, and then x1, y1. Okay, and then you have the second entry. The second entry will be y2 times this p of x1. Oh, I'm missing something here. So the first entry would be this times this plus y2, and then you have pxy, x2, y1, and so on. Okay, so that would be a very, very long sum, but anyway, it will sum up to a number. If I want to write it in terms of a shorthand notation, then this entire sum, which is this number times this, that number times that, and so on, I can really write it as the summation of this p of x1, okay, because the 1 will stay there, and then I have the y j's, and then I have this small yj's, and j will go from 1 to n. That would be my first entry. The second entry would just be y j again, p, and then here will be x2 and yj. So you continue this calculation, that will give you a column vector by just calculating this product, okay, between p and y. Now let us also do the outer multiplication where you have x. So you have x1 times this number, so that will give you this summation of xi's, and then you have this inner summation, it will be yj's, and then your pxi, and then yj. Okay, so that will give you the overall number. You have summation over I, summation over j. But since these two summations are independent, you can just write it as summation I and summation j and xi and xj of your pxi and yj. Okay, so you see that if I have this matrix times this vector, and then I have an outer vector, take the transpose multiply together, I will eventually get not a vector, I will get a scalar, and then the scalar will be given by this expression, which is exactly the same as what we want for the joint expectation. Okay, so what is the story here? The story here is that if you look at this expectation of x times y, you can really treat it as the this matrix vector multiplication. Now, of course, you have a p here, but let's pretend that the p doesn't exist here. What is this? This is the inner product between two vectors, x and y. And what is the meaning of inner product? The meaning of the inner product is to see how close is one vector compared to the other. And that is measured in terms of the projection or a concept we call the cosine angle. Okay, so what I want to do next is to go a little bit deeper into this equation here of x transpose py and explain further what is the meaning of this joint expectation between x and y. Okay, so here it is a small detour to linear algebra. I hope it wouldn't be too new to you because most of these concepts has been taught in the freshman or sophomore linear algebra course. Okay, so you can treat it like a review of the concepts. If you have two vectors x and y, you can define a thing called the cosine angle, cosine theta. Okay, it's called a cosine angle. And then this cosine angle is defined as the ratio between the inner product x and y, x transpose y, divided by the norm of x and the norm of y. Okay, the norm of x is just the square root of some square. Norm of y is the sum square. Take the square root. What is the meaning of this cosine angle? Well, you have this vector x, you have this vector y. Cosine angle is measuring the angle between x and y. Now, if your x is parallel to y, okay, what does it mean? Well, it means that x and y, they are completely correlated. In that case, this cosine angle will give you, this theta would be 0, and cosine theta will go to 1. And so you can see that x and y, this cosine angle will go to 1, and that indicates that your x and y, they are completely correlated. Now, when will you have them being uncorrelated? It would be that your x is perpendicular to your y. In that case, when you take the inner product, x and y, you will get 0, and you can say that in this case, my random variable x and y, they are uncorrelated. So there is a very beautiful geometry behind this expectation of x times y, because if expectation of x times y is the cosine angle, and cosine angle is measuring the correlation between the two vectors, then precisely this expectation of x times y is telling you the correlation between the two random variables. Now, of course, there's some subtlety here because this cosine angle is between x transpose and y. There's really no P matrix that's what we are defining here. So what we want to do is to think about a little bit deeper of what's happening with this P of xy, okay, and then Px and Py, because we haven't really defined the correspondingly what are these terms. So let us try to think about what do we want for the joint expectation. Okay, so the joint expectation, remember that it is expectation of x and y. That is defining the inner product of x, p, and y. This thing itself is not yet the cosine angle. To get to the cosine angle, we need to take the denominator of x, okay, and then we need to take the denominator of y. But we need to take a little bit care because this is the Pxy matrix. That is the joint PMF between x and y. So when we take the expectation of x here, this has to go with the Px, and this has to go with the Py. These are the marginal PMFs of x and y independent, okay, respectively. And now this is the numerator, and so the denominator has to be something like this. And it turns out that this is just the expectation of x squared, and here it would be the expectation of y squared. And then when we take the square root, you will be able to get this thing called a cosine angle. Okay, so the cosine angle is like a normalized version of the joint expectation. And in this case, we have seen the meaning of this Pxy, and now we also want to understand a little bit about this, the Px and Py. They're the joint, no, they're the marginal PMFs. So in this slide, I'm showing you the meaning of this Px and Py. Now we can start off with this term the expectation of x squared, you can write down the definition. It will be summation of x squared times your marginal PMF. And how to calculate this? Well, I can construct a matrix, Px, which is a diagonal matrix. Along the diagonal, I have all the PMF values. And then I have this column vector of x that contains all the elements, x1 through xn. And then here I have another row vector contains x1 through xn. If I do this matrix vector multiplication, I will be able to recover this summation, because you can follow this calculation px1 times x1, px2 times x2, and so on. And you sum them up, you will get to this summation. Now, this can be written as the matrix vector multiplication of x transpose px and x, and we can define it as the norm square with a weight. The weight would be this px, and that's why we have this px here and we have this py here. So the bottom line message of this calculation is really to convince you that the correlation, which is defined as the expectation between x and y, is forming the numerator of this cosine angle. You need to do the normalization. The normalization would be the individual norms of x and y. Okay, and so this slide will summarize what we have seen so far. So the cosine angle is given by this expression, okay, and then this expression really means this term. So what is x times y then? So this expectation of x times y is the cosine angle between x and y. Well, of course, I need to be careful. It will be divided by the expectation of x squared and then expectation of y squared. So that's to be the normalized version of the covariance, the correlation. Okay, so that would define the cosine angle, and this will measure how similar x and y are. And so now the new thing here, it will be slightly interesting, is to realize that the presence of these matrices. These matrices, they are the weight that goes with the vectors. Now, of course, if your pxy and px and py, they are all uniform, then you will recover the same the usual cosine angle without the weight. Okay. However, we all know that in probability, different states have different weights, and therefore you want to weight them differently. That goes to the reason why we have this px and py. And because of all these reasons, you can see that this term, which is the normalized version of the correlation, it has to be between -1 and 1. Why? Because this is defining the cosine angle. And the cosine angle, by definition, it has to be between -1 and 1. You can never go above 1. You can never go below -1. Now, of course, if you want to be a little bit more rigorous, you can try to prove this result, meaning that you want to prove that this ratio is always between -1 and 1. And how to do that? You can prove a thing called the CauchySchwarz Inequality, which we are not going to prove here. You can refer to the ebook for the entire proof. The result says the following. You look at the expectation of x and y, you take the square outside. This is upper bounded by the product of the second movement. Okay, so you have expectation of x squared, expectation of y squared. Now, if you can prove this Cauchy-Schwarz inequality, then you can just move this term into the denominator. Then you have this thing square. It will be less than or equals to 1. Then you remove the square sign. Then you'll be able to prove the other sign, which is -1. Okay, so this is the Cauchy-Schwarz inequality. It is a very useful inequality. In the next lecture, we will come back to this point again. We want to look at is there any a way that we can compute this in practice. And furthermore, is there any relationship between this quantity to a pair of random variables that are independent? So that would be the objective of the next lecture. So this is the end of today's lecture. I hope you have learned something, which is hopefully it is new to you. And to me, this concept of joint expectation and understanding the origin of this joint expectation through the perspective of the linear algebra and understanding the inner product cosine angle, this is very, very useful. It helps you to understand that the joint expectation is not just a formula of expectation between x times y. It is actually having a very, very deep geometric meaning. And that will help you understand a lot of these calculations. So if you have any question, I will encourage you to post your question on our Piazza forum. Please also try to read the ebook. It contains a lot more details than this lecture slides. Furthermore, we will have homework problems on joint expectations. I hope you will enjoy the problem. Thank you very much.